Hi. In the previous lecture, we built a mechanical picture of Earth's interior, a strong, rigid lithosphere overlying a weaker, warmer asthenosphere capable of slow flow. Today, we build directly on that framework. Plate tectonics describes how the lithosphere is broken into large, rigid plates that move slowly over the asthenosphere. These plates behave as coherent units, meaning they do not deform internally very much compared to the narrow zones where they meet. As a result, most geological activity that shapes Earth's surface, faulting, volcanism, earthquakes, and the creation and destruction of ocean crust, is concentrated at plate boundaries. In this lecture, we will focus on how plates move, what forces act on them, and how different types of plate boundaries shape the ocean basins. A plate boundary is defined by how two plates move relative to one another, not by whether the boundary lies beneath an ocean or beneath a continent. It's the geometry of motion that matters the most. There are three fundamental types of relative motion. A divergent boundary is where plates move away from each other. At convergent boundaries, plates move toward each other. At transform boundaries, plates slide horizontally past one another. Each of these boundary types produces a distinct mechanical response in the lithosphere. Those mechanical differences control where crust is created, where it is destroyed, and where deformation is focused. In the rest of this lecture, we will examine each boundary type in terms of the physical processes taking place and how those processes shape the ocean basins. When we draw plate motion on a map, it often looks like plates are sliding in straight lines. But in reality, plates move across the surface of a sphere, and that changes how motion works. A useful way to think about this is to imagine pushing on a globe. You cannot move a rigid object across a sphere without rotating it around some axis. The axis of rotation is called an Euler pole. For each plate, there is a specific axis about which it rotates relative to other plates. Because the plate is rotating, different parts of the plate move at different speeds. Points close to the Euler pole, as indicated here, points close to the Euler pole move very slowly, while points further away move faster. The direction of motion also changes along the boundary. This variation in speed and direction explains why plate boundaries are often broken into segments, why mid-ocean ridges are offset by transform faults, and why a single boundary can show different behaviors along its length. So in this illustration here, plate M is moving in the direction to the bottom and to the left, centered around this Euler pole. So points are parts of the plate that are closer to this center of spin is going to move slower, whereas parts of the plate that are further away from the center of spin will move much faster. So in essence, parts of the plates are moving in different speeds. Now that we understand how plates move geometrically, we can ask a more fundamental question. What actually causes the plates to move? Plate motion results from a balance between forces that drive motion and forces that resist it. The strongest driving force is slab pull. Here, the term slab refers to the portion of a tectonic plate, usually old oceanic lithosphere, that is sinking into the mantle at a subduction zone. As this cold, dense lithosphere sinks under its own weight, it pulls the rest of the plate along with it. Another driving force is ridge push. Mid-ocean ridges are elevated because newly formed lithosphere is hot and buoyant. As this lithosphere cools and thickens away from the ridge, gravity causes it to slide slowly downhill. This gravitational sliding pushes the plate away from the ridge axis. Plates also interact with the flowing mantle beneath them through a process called mantle drag. The asthenosphere is not stationary. It flows slowly as part of mantle convection. As a plate moves over this flowing mantle, the mantle can either help carry the plate along or oppose its motion, depending on whether the mantle flow is moving in the same direction as the plate or in opposite direction. Opposing all of these driving forces are resisting forces. These include friction along plate boundaries, the energy required to bend a rigid plate downward into a subduction zone, and buoyancy forces that resist sinking. Especially when continental lithosphere is involved, plate motion reflects the net outcome of these driving and resisting forces acting together. At divergent boundaries, tectonic plates move away from one another, placing the lithosphere under tension. As the plates separate, the lithosphere thins and fractures, creating space at depth that must be filled. Hot mantle material from below rises upward in response to this separation. It is important to note that the mantle is not rising because it's being heated at the ridge. It's rising because the plates are pulling apart and material must move in to replace what is being removed. As this mantle material rises, the pressure acting on it decreases. Even if the temperature remains essentially the same, this drop in pressure allows part of the mantle to melt. This pressure-driven melting is called decompression melting and is the fundamental process responsible for magma generation at mid-ocean ridges. The magma produced is basaltic. It rises through fractures in the lithosphere, it cools, and it solidifies to form new oceanic crust. As spreading continues, this newly formed lithosphere is carried away from the ridge axis where it cools, thickens, and becomes more dense. Over time, this process produces the characteristic pattern of young, shallow seafloor at ridges and progressively older, deeper seafloor further away. Mid-ocean ridges are the surface expression of divergent plate boundaries, but they are not uniform features. Their structure reflects how extension is accommodated in the lithosphere and how much magma is supplied from below. Near the ridge axis, heat flow is very high because newly formed lithosphere is hot and thin. Some extension is accommodated by volcanic activity as magma rises and solidifies to build new crust. At the same time, extension is also accommodated by normal faulting, where blocks of crust drop downward as the lithosphere is pulled apart. This can be visualized if you think about a time where you split a cracker into a few pieces and notice crumbs fall to the floor. That's the sort of faulting that we're talking about here. The combination of high heat and abundant fractures allows seawater to circulate through the crust. Cold seawater penetrates downward, is heated by the rock, reacts chemically with the basalt, and then rises back to the seafloor in hydrothermal vents. These systems transfer heat and chemicals from Earth's interior into the ocean. The appearance of a mid-ocean ridge depends strongly on spreading rate. At fast-spreading ridges, magma supply is relatively continuous, so volcanic construction dominates, and the ridge crest is smoother and broader. At slow-spreading ridges, magma supply is less continuous, and its tension is taken up more by faulting, producing a deeper rift valley and rougher topography. At transform boundaries, tectonic plates move horizontally past one another. This sideways motion is fundamentally different from the separation that occurs at divergent boundaries or the compression that occurs at convergent boundaries. Because the motion is horizontal, transform boundaries do not create new lithosphere and do not destroy existing lithosphere. Instead, they serve to accommodate lateral motion between plates that are moving in different directions or at different speeds. Deformation at transform boundaries is concentrated along narrow, near vertical fractures in the lithosphere called strike-slip faults. As plates attempt to slide past one another, friction along these faults resists motion. Over time, stress accumulates until it is released through sudden slip along the fault. Although transform boundaries are often associated with earthquakes, their broader role in the plate tectonic system is geometric. They allow plate motion to remain continuous across Earth's curved surface by linking segments of divergent and convergent boundaries. Without transform boundaries, the global pattern of plate motion would not be mechanically possible. When we look at the ocean floor, transform boundaries appear as long, linear features that can extend for hundreds or even thousands of kilometers. However, only part of the feature is an active plate boundary. A transform fault is the segment of the boundary where two plates are actually sliding past one another in opposite directions. This is where stress accumulates, where the slip occurs, and where earthquakes are generated. Transform faults are therefore active features in the plate tectonic system. Beyond the ends of the transform fault, the same linear feature continues across the seafloor as a fracture zone. In a fracture zone, both sides of the features belong to the same plate and move in the same direction at the same speed. Because there is no relative motion, fracture zones are not plate boundaries and do not generate earthquakes. Fracture zones remain visible on the seafloor because they juxtapose crust of different ages, temperatures, and elevations. In this way, they preserve a record of past plate motion even though they are no longer tectonically active. At convergent boundaries, tectonic plates move toward one another. Because plates are rigid, this motion cannot continue indefinitely without something giving way. Convergence must therefore be accommodated either by one plate sinking into the mantle or by significant deformation of the crust. The outcome of convergence depends primarily on the type of lithosphere involved. which controls density and buoyancy. There are three main possibilities. When two oceanic plates converge, the older, colder, and denser plate sinks beneath the younger plate. This process forms a deep-sea trench and leads to the development of a volcanic island arc above the subducting plate. This type of convergence commonly occurs in the open ocean. When oceanic lithosphere converges with continental lithosphere, the oceanic plate subducts beneath the continent because it is denser. This produces a trench offshore and a chain of volcanoes on the continent, forming a continental volcanic arc. This process plays a major role along many continental margins. When two continental plates converge, neither plate readily sinks because continental lithosphere is relatively buoyant. Instead, convergence is accommodated by crustal shortening and thickening. The crust is folded and faulted, producing high mountain belts rather than deep trenches or extensive volcanoes. In the context of oceanography, convergence involving oceanic lithosphere is especially important because it leads to subduction, which is the primary mechanism by which oceanic crust is recycled back into the mantle. When convergence involves oceanic lithosphere, the dominant process is subduction. Subduction begins because oceanic lithosphere becomes denser as it cools and ages. Once it is sufficiently dense, it can sink into the underlying mantle under its own weight. At the plate boundary, the oceanic plate bends downward as it begins to sink. This bending of a rigid plate creates a deep, narrow depression at the surface, which we observe as an ocean trench. The trench marks the location where one plate starts to descend beneath another. As the plate continues to sink, it remains relatively cold and mechanically strong compared to the surrounding mantle. Because of this, it fractures as it descends, producing earthquakes along a dipping zone that traces the path of the subducting plate into the mantle. This sequence, plate convergence, bending, trench formation, and slab descent, defines the mechanical foundation of subduction zones and explains why trenches and deep earthquakes are closely associated with features in the ocean basins. One of the most common misconceptions about subduction zones is that the descending plate melts and directly feeds volcanoes. In most cases, that is not what happens. The subducting oceanic plate is relatively cold compared to the surrounding mantle and does not simply melt as it sinks. As the slab descends, however, it is subjected to increasing temperatures and pressure. Minerals within the slab that contain water and other volatile components become unstable and will break down. This process releases water from the subducting plate into the overlying mantle. The mantle above the slab, called the mantle wedge, is normally hot but solid. When water is added to this mantle material, it lowers the temperature at which melting can occur. As a result, part of the mantle wedge begins to melt, even without an increase in temperature. The magma produced by this melting is buoyant and rises through the overlying plate. Over time, repeated eruptions build a chain of volcanoes known as a volcanic arc, located at a characteristic distance from the trench. This explains why subduction zones are consistently associated with volcanic arcs rather than random volcanism. A subduction zone is not a single feature, but a linked system of regions that reflect different physical processes operating above and around the descending plate. Closest to the plate boundary is the trench, which marks where the oceanic plate bends downward and begins to sink into the mantle. Sediments carried on the oceanic plate may be dragged down with it, but in many cases they are scraped off and accumulated into a wedge-shaped body called an accretionary prism. Landward of the trench and accretionary prism lies the forearc region. This area sits above the plate interface but generally lacks active volcanism because it is positioned above relatively cool parts of the system. Further inland is the volcanic arc, which forms above the region where water released from the slab triggers melting in the mantle wedge. The position of the arc reflects the depth at which these melting processes occur, rather than the exact location of the plate boundary. In subduction zones, extension occurs behind the volcanic arc, forming a back arc region. This can happen when the subducting slab rolls backward, creating space in the overriding plate. In oceanic settings, back arc extension can even lead to the formation of a new seafloor. Up to this point, we have focused on volcanism that occurs at plate boundaries such as mid-ocean ridges and subduction zones. However, not all volcanic islands form at plate boundaries. Some volcanic islands form in the interior of tectonic plates, far from any plate boundary. These are associated with what we call hotspots. A hotspot is a location where melting occurs repeatedly in approximately the same place for a long period of time. The most common explanation is that hot material rises from the deep within the mantle, supplying heat that promotes melting beneath the lithosphere. Importantly, the tectonic plate above the hotspot is moving, but the melting source itself remains relatively stationary compared to the plate. As a tectonic plate moves over the persistent source of melting, magma rises through the lithosphere and erupts at the surface. Over time, repeated eruptions build a volcanic edifice on the sea floor. If eruptions continue long enough, the volcano can grow tall enough to rise above the sea level, forming a volcanic island. This process does not happen just once. As the plate continues to move, the volcano that formed above the hotspot is carried away from the melting source. Once it moves off the hotspot, magma supply decreases and volcanism shuts down. The island then begins to cool, erode, and slowly subside. Meanwhile, a new volcano begins to form directly above the hotspot, where melting is still occurring. The result of this process is a chain of volcanic islands and seamounts, arranged in a line that reflects the direction of the plate motion. The key feature of these island chains is that they show a systematic age progression. The youngest volcanic activity occurs at the island currently above the hotspot, while islands become progressively older with increasing distance from that point. The Galapagos Islands provide a clear example of this process. The Galapagos hotspot is located beneath the Nazca Plate. As the Nazca Plate moves east-southeast, volcanic islands form above the hotspot and are then carried away. The western islands of the Galapagos are volcanically active today. while islands farther east are older and volcanically inactive. In addition to forming islands, hotspot volcanism builds large volcanic structures on the sea floor, including sea mounts and broad swells in the oceanic crust. These features contribute directly to ocean basin topography and provide another way to trace plate motion through geologic time. In this way, hotspot island change serve as a record of plate motion, complementing what we learned from plate boundaries and helping us understand how volcanic processes shape the seafloor far from tectonic margins. I encourage you to pause the video for a moment to carefully review both illustrations that highlight the hotspots that are creating the Galapagos Island chain as well as the Hawaiian Island chain. We now have enough information to understand how new ocean basins form. So let's take a look at this before we finish today. To do so, we need to look at what happens when continental lithosphere is pulled apart. This process is known as continental rifting. When continental lithosphere is placed under tension, it begins to stretch. Because the lithosphere is rigid and relatively thick, it cannot stretch smoothly. Instead, as it is pulled apart, it becomes thinner and mechanically weaker, and cracks develop as the crust adjusts to the stretching. As the lithosphere thins, the surface begins to sag, forming long, narrow depressions within the continent. At the same time, thinning reduces the pressure on the hot mantle beneath the lithosphere. This reduction in pressure is important. As mantle material rises closer to the surface beneath the thinning lithosphere, pressure decreases and partial melting can occur through decompression melting, even if the temperature does not increase. This is the same fundamental melting process we discussed at mid-ocean ridges, but here it occurs beneath a continent rather than beneath the ocean. If rifting continues, magma produced at the depth can move upward and add heat to the thinning lithosphere, further weakening it. Eventually, the continental lithosphere may break apart completely. When this happens, the two pieces of continental crust separate and a narrow ocean basin forms between them. At this point, the tectonic setting changes. Instead of continental rifting, the system transitions to seafloor spreading. A mid-ocean ridge develops, new oceanic lithosphere begins to form, and the ocean basin widens over time. Now, some rifts never reach the final stage, but instead they remain as a failed rift within the continents. Others succeed and become the sites of new oceans. This process explains how entirely new ocean basins can originate from continental interiors. Now that we have examined the major plate boundary processes, divergence, transform motion, convergence, hotspots, and rifting, we can step back and consider their combined effect on the ocean basins. Plate tectonics does not simply move pieces of the lithosphere around. It continuously creates, modifies, and recycles oceanic lithosphere. New seafloor forms at mid-ocean ridges. As that lithosphere moves away from the ridges, it cools, it thickens, and it becomes denser, causing it to subside to greater depths. This process produces predictable depth patterns across the ocean floor. Transform boundaries leave linear scars on the seafloor where crust of different ages and elevations are juxtaposed. Subduction zones create the deepest features on Earth, ocean trenches, while also building volcanic arcs and broad regions of elevated topography. Hotspot volcanism constructs isolated volcanic islands, sea chains, or seamount chains, and broad swells in the oceanic crust. Taken together, these processes explain why the ocean floor is not flat or uniform. Instead, ocean basin topography reflects the age of the seafloor, the type of plate boundary present, and the tectonic history of each ocean. In other words, the shape of the ocean basins is a direct consequence of plate tectonic processes acting over geologic time. I'm going to hold this image on the video for 30 seconds, but I encourage you to spend even more time on this important illustration that summarizes the processes we have been covering today. So pause the video for a few minutes and see if you can explain and understand all of the processes labeled in the diagram. And especially take some time to reflect on the influence that has on the ocean basin topography. In this lecture, we focused on how tectonic plates move and how plate boundaries create, modify, and recycle oceanic lithosphere. The next step is to connect these processes directly to what we can observe on the seafloor. The ocean basins are not flat surfaces. Instead, ocean depth varies in predictable ways that reflect how and where the seafloor formed, how old it is, and what tectonic processes have acted on it since its creation. Mid-ocean ridges form elevated features where new lithosphere is created. As seafloor moves away from the ridges, it cools, thickens, and subsides, producing progressively deeper ocean depths. Subduction zones create the deepest trenches on Earth, while hotspot volcanism builds seamounts and island chains and broad swells on the ocean floor. In the next lecture, we will focus explicitly on ocean topography using bathymetric data to examine the shape of the ocean basins and to interpret how plate tectonic processes have shaped the seafloor today.